So this is the show 11th show of this season, and we again planned for about 3 or 4 new questions. It depends on the time. If we go with 3 problems or we go with 4 problems. And before we do it, we want to revisit that simple question actually we covered the last time, and just spend 1 minute on that. Ivan, you want to show us that question?
Yes, surely. Okay, so the question was by Chris. It was about finding
the two,
7.
right? Because last time students made some comments about this is trivial, blah, blah, blah. Well, maybe it is on the easy side for Amy question or so on, which I also agree. But I do think when we ask a question to the audience, we got lots of feedback and we realized actually students might miss some important thing here. We posed a question to the audience, how to make this problem harder. I think many of the feedback we got is the first thing they point out is they want to say, oh, let's make 71 into a number with lots of factors. And that comment actually is a little bit alarming because people think they solve this question is easy because 71 is a prime. And I think at the end of the show, that discussion, Ivan said something, but I think it might fall into cracks and people didn't listen carefully. Actually, Ivan, what did you say? Can you start to repeat that part?
Well, I think it would be better, well, if it has lots of divisors, it's not a problem.
Let's say it's 98, 99, and 100.
They're consecutive.
Yeah, 3 consecutive, 90, 98, 99, 100. Okay. Actually, this still doesn't make the problem any harder, but you have to solve it slightly differently, right?
Correct, but you still look for the common divisors. So C divides both of these numbers. So C divides both 98 and C divides 99, right?
Mm-hmm. Yeah.
So which means how it could be, C is a common divisor of 98 and 99. The only way it's possible, C must be equal to 1.
Yeah. So even though this is a simple question, and then sometimes students are so happy to say they got an answer, but they didn't realize the 2 slightly different solutions for this question. One is say, okay, I look at this original question, I say, okay, 71 is a prime, so I know C is 1 and E is 1. And another solution is saying, okay, I look at it, these 2 are consecutive numbers, now I know C divides their difference, which is also 1. They are both very simple, but one reasoning is much more powerful than the other, could help you to solve other questions, right? I just want to point this out. Don't let students completely just say, oh, this is trivial and let it go, because you always can get something out of it, right?
Yeah, I found just looking at various problems that sometimes just the simple observation that 2 consecutive integers are relatively prime, that can actually sometimes be a very powerful thing to break the problem open. Yeah. And even a little bit beyond that, in case you haven't seen it, 2 consecutive Fibonacci numbers are relatively prime. Mm-hmm. If you haven't seen that one, you should be able to prove that one pretty easily, right? So, yeah, but that was these kind of off-the-cuff remarks. That's kind of what makes these interesting. You never know what people are going to think or say. So that was a good remark, Ivan.
Yeah, so that's what we want to go. That's why we want to do this one.
Yeah.
And then we can go back to the new question this time, right? Ivan, are you ready for show us the question? You want to do a poll?
Okay. The poll is what? Where it was proposed?
Sure.
Or who is the proposer?
I think who is the proposer is better, because in the beginning we have lots of guessings can go around.
Okay. So while people are voting, we can read this problem.
If I can just say a little spoiler, do we ever do a poll where we have someone whose name is on there who's not on the panel? I don't know.
Sometimes, yes. Well, James is not here, but he should be here.
Yeah.
Evan's not here. Like maybe Evan wrote it. you know?
Yeah, we could discuss someone's problem too.
So we can end the poll here, and Chris is winning, but that's the wrong answer. Actually, I wrote this one, right? So let me read this one. How many odd positive three-digit integers are divisible by 3, but not contain the digit 3? Just short little counting problems. And students doing AMC 8 will be so happy to do this kind of problem because they are very good at listing. So the listing approach is about what? You basically can say, okay, let's find all the numbers, odd numbers that are divisible by 3, right? How many are there? There are 900 numbers. There are 900 three-digit numbers, right?
Mm-hmm.
How many of them are divisible by 3?
A third.
A third of them. And how many of them end with even digits, I think? They want odd numbers, right? So it's every 6 of them, right? So it's all divisible. Yeah.
150, okay, numbers that are odd and divisible by 3.
Divisible by 3. Well, then after that, we can start listing, right? If there are people who, all this, math count skill and AMC 8 skill comes in, you can have what? You can have bad numbers of what situation? It's like 3AB, A3B.
So we start to lead bad numbers. 3AB,
right. A3B, and AB3. And then this is assuming what? AB don't have 3, right? Mm-hmm. Or they can have 3. And then you overcount what? Those, 3 threes, right?
3x, 3y's 3, z 3.
And then finally is what? 3, 3, 3, right? Mm-hmm. So you can do all those listings, right? And if you're careful enough, then you'll be okay. But of course, that's kind of like very tedious, and you don't want to do that, right? So this kind of problem, if it happens on the mass count countdown, if you list like this, you're in trouble. So what's the better way of doing this? Is basically you're looking at this A, B, and C, what do we think? What are the conditions we have to worry about? We have to worry about the first digit because they cannot have 0. Right? And we have to
also can't have 3.
Yes, and 3. Good. And the last digit also cannot have what? Last digit have very limited choices. It's
1579.
579. Yeah, 1579. 4 of them, right?
1579. Yes.
So counting is usually deal with those bad conditions first, and then come back to this B that's only have with what? No restrictions at all, except it cannot be 3. Mm-hmm. Right? So Alex, what will you do it?
What?
How do you do to finish?
Well, I mean, if you just get rid of the divisible by 3 condition, you have 8 times 9 times 4, right?
Yes.
8 times, so
8 times 4 times 9, maybe it's better.
8 times
9 there.
9 there.
Times 4 without restriction for digit 3, right?
No, without divisible by 3.
Without divisibility by 3, yes.
So divisible by 3, like it should be around 1/3. So what you want to do is you want to find a number here that's divisible by 3, which is B. This 9 here, right? So this 9 hopefully splits into like 3, 3, and 3 based on what A and C are.
Yes.
And so you can do an example, right? You can choose A and C first, and then you can see how many possibilities there are for B after you choose A and C.
First, and then you can have B to be what? 0, 6, 9.
Yeah.
1, 4, 7, and B, which is 2, 5, 8.
You want to write the middle one instead of A is B.
Sorry.
B. Yeah.
Okay.
And they are evenly distributed, right?
Mm-hmm.
And when A and C is to check if the number is divisible by what? 3, you basically want what? You can choose A and C freely, and you want to make sure your last number, make sure A plus B plus C is what? Is divisible by 3, right? But now your things are equal. So all of them have equal chances. So it's exactly 1/3 of that, right?
12 by 8.
Yeah, 96.
Cool.
Yeah. So that covers our introduction problems. So now we move on to our what? The next one?
Yes. So this is the next one.
So let's do another poll. Let's see where this problem is from. From which test?
I think many people will figure out.
Really? Let's see.
Okay, many voted. 80% voted.
80% voted, but hardly anyone got it right. You know why? Because actually the statement of the problem make you feel like it's Amy because of what? They ask for some kind of integer, right? The actual answer is like something root A plus root B or whatever. And see, this is very interesting. Our students all take AMC tests, but I think more of the time they only care about what? Oh, I got a 120, I'm happy. They never really look at the 4 questions they never solve. So that's very bad. This is one thing I really think our students can improve a lot by just solving some older test problem is really solving them, the hard one they could not solve. Because this is our audience coming from students are very into contests, right? And they just took AMC 2018, and this is number 25, and they didn't recognize. So that's kind of like that. Well, whatever. Okay, David, you have the floor. It's your question. Wonderful.
Yeah, all right. So let me get this all set up again. Okay. So sharing the screen.
I think it's a wonderful problem because it's so hard to ask a simple question. And the question is so simple. You have 3 circles with radius 4. And you construct this triangle such that it is tangent, kind of cyclically tangent, right? To 3 of them. Yeah. And you want to find its area.
Yeah, I'll say this is one of my favorites. This is definitely one of my all-time favorite problems. Also, if you're familiar with my work, you may realize that it's kind of weird that I'm only just now getting to a geo problem when the vast majority of the problems I write are geo. So I'll talk more about that and sort of the inspiration behind this problem later. Though the TLDR is there's not much inspiration, but the backstory is kind of interesting. In terms of the solution, it turns out there is an extremely short solution to this problem that nobody found. I only found out about it. My original solution was ridiculously complicated, and I only found out about the solution in the AOPS math jam. So
I have a different answer after I printed out this afternoon. I will share with you. So go ahead. Yeah.
Sure. So let's look at. Let's draw. So this is the solution I did not find. Let's draw the centers of these circles, right? So what do we know? The key observation is to look for tangencies, and there are lots of them. So in particular, if I draw this line over here, and I'm going to draw this line over here, and you know what? We have 2 circles. Let's draw the line connecting their centers. Okay, so let's figure out what we know. We actually know the lengths of all three of these segments. It's actually pretty easy. What are the lengths of the lengths of the red segments are 4, because that's what we're given. They're given the radius of the circle is 4. What is the radius? What is the length of the blue segment?
8.
It's
Because
8.
tangents.
Yeah,
tangent
because it's just the sum of the radii of the two circles. Okay, so it turns out we're not almost done. But we're actually like we're getting pretty close. So what I'm going to do, and this is the really clever part that I did not notice the first time I tried this, is to drop this perpendicular down. Okay, so this gives us 2 segments. It gives us a pink segment and a purple segment. So, okay, this diagram's a little bit crowded. I'm going to zoom in.
Well, David, I can tell you why it could make sense, because if you look for angles, you probably can predict that P1, P2, P3 is equilateral.
Yeah,
So
P1, P2, P3 is pretty obviously equilateral, but basically it's a symmetry argument.
And you mark 90-degree angle, so there is that red angle that is 30 degrees. So I would have that 30 degree in my diagram, definitely.
Yeah, I was just going to draw that, but I could not fit the 30-degree angle inside, so I'm zooming in. That's all. So let's see. This is 30 degrees right here. And just to be clear, that's because this is an equilateral triangle, so that's 60 degrees. Okay, so what is the length of the purple segment?
4/√3, right?
The purple segment, not the pink segment.
2.
It's just 2.
Okay.
It's just 2. What about the length of the pink segment? The length of the pink segment is 2 times √3.
Mm-hmm.
So, okay, that's cool. If we can figure out the length, we've already got one length of the side of the equilateral triangle. If we can figure out the rest of the rest of the things, we're done. And it turns out we can do this by just making a simple yet kind of brilliant auxiliary construction. Let's do this. I'm going to extend the radius from P1 and intersect it with, I'm going to construct this point such that this is a rectangle. So the green thing is a rectangle. Let's call this point X. Okay. What's the length of P1X? 2.
Well, I don't think you even need to construct X. You already have a pair of similarity. You can get everything.
That's true.
The 8 is already being cut into 2 to 1, right?
That's true. Yeah. I think basically once you figure this,
once you figure out whatever you are doing, it's no difference. Yeah.
It's basically exactly the same. Yeah. So, but this is 2, and then what's the length of the other green segment? Sorry, we don't know that yet. Actually, yeah.
Well,
so
but you know 8, right? Yeah, you know green segment. Yeah, because
the blue is the length. The length of the blue segment is 8, but we can compute this length of this segment.
Yeah.
8 minus 2√3.
It's by Pythagorean theorem on this
On
this big black triangle right here.
Yeah.
So that's equal to the square root of 8 squared minus 6 squared, which is 2√7, if I remember correctly. Yeah, because it's 2 times square root of 4 squared minus 3 squared. So that we're done, because that tells us that the side length of the triangle is 2√3 plus 2√7.
Yeah. Wow.
And now we can get the area. Area equals s squared √3/4, which conveniently the 2 will cancel out with the divided by 4, and what we're left with is square root of 300 plus the square root of 252. And the reason I read it this way is because that's the way of the answer choice. That's the way that the AMC worded it. In particular, the problem asks to find m plus a plus b, where you write it in the form root a plus root b. So that's why I'm writing it this way. Yeah. So as I said, this is one of my favorite problems, precisely for the reasons that Yvonne suggested. It's a really short problem statement. it's a really natural problem statement. I really love natural problem statements, and its solution isn't obvious. So how did I come up with this problem? So the story goes that the reason this problem came up was because I was a freshman in college. So I had been in college for about 2 weeks or so. And I was still trying to get used to the environment. I was still trying to get used to the college environment. So one thing I used to do when I was beginning in freshman year was because I was very concerned that when I was doing my laundry, I would forget that my clothes were in the laundry room and just completely forget about them, which is, very, very distressing to a first timer in college. So I used to go down to the lounge and completely not bring my computer, not bring anything like that, just sit down and work on something. So I was down near my laundry so that I wouldn't forget it was there. And one time I decided I was going to write a math problem. This is the math problem that came up. So that's kind of my one of my two funny this circumstance led to one of my favorite problems. The actual story behind the problem is actually not that interesting. I just drew the 3 circles and eventually came up with the equilateral triangle, which is kind of anticlimactic, but also I'd argue that most problems that I've written are very anticlimactic, which is kind of infuriating because sometimes you're just oh my gosh, I came up with this. I've been thinking about this problem for hours and I haven't been able to get anything useful out of it. But then sometimes you just come up with the right idea and it's your first try and you feel so happy because you figured it out. And it's so infuriating sometimes. Consistency would be so great, but it's not, which is kind of the point, but also really infuriating. Yeah, that's my spiel.
This is Chris here. If I can just say a word or two about my problem creation process. I think I mentioned in a previous episode that a lot of my problems are born on airplanes because I'm sort of stuck there. I can't really do much. And so I kind of just get out a sheet of blank paper and doodle. And, sometimes a lot of what I do doesn't really lead to anything. But sometimes I get very surprised and I notice something interesting. And there's something about your intuition. I get this sense, when I have something nice and I've locked in on it, I sort of know it. I'm like, yeah, this ought to be good. Sometimes people say, oh, yeah, that's too easy or it's too guessable. But yeah, that's often led to just very serendipitous, I guess, is my creative process. But the airplane is my creative zone for some reason. So
actually, yeah, I remember in particular that you mentioned this whole intuition thing. I remember specifically thinking as soon as I drew this diagram, I was like, wait a sec, this could be a really, really good problem, and I was extremely motivated to solve it. So I could just tell that this was going to be something interesting. My official solution ended up being extremely complicated, but that doesn't matter. That's what the committee's for.
Also, another thing I'm often inspired by, and many contest takers will know this, is when we weave the current year into the problem. I mean, it's gotten to the point where people are like, okay, you should memorize the prime factorization and you should memorize all these trivia points about the current year. But that can sometimes constraints or just, being inspired by something can lead very accidentally almost to an interesting problem. So, yeah, anyway.
So right now, Chris, you're having trouble to write problems because you cannot fly. But David can still write his problems because he can go to laundry room, right? So David
I mean, the laundry room in my apartment is not really an optimal place to be. Let's just say that.
Okay.
No, I'll do some laundry and see if I can write some problems.
Yeah. But I have a question for our audience for this question. I think this question is actually very, in a certain way, I think it's it's misused for AMC, because I think the best part of this problem is for our audience to really show this, how do you construct this triangle.
Oh, you mean with a straight edge and compass?
No, not even that. Really ask our students is, why such a triangle exists and in what way you should be able to construct it. Yeah, I'm not talking about strictly talking about straight edge or compass. I'm more into is okay. Give me a process about locating these 3 points. I think that's more interesting because whenever it becomes an AMC question, there are lots of parts you start to be guessing. You can even say, oh, it should work that way. Because my solution is longer, I used the center of this whole 3 circles, that thing which will be the center of P1, P2, P3, because I know by similarity they should do that way and then compute. But I never really, even from the beginning, I would say, okay, how do I really find these 3 points? Because the other computation I have somehow have to use the fact that coming from the center of this whole diagram and construct certain angles to get those P1, P2, P3. I'm more interested in really how to see this from the very beginning to say geometrically to say I can locate these points. So in that way, I feel like, for math reasoning, this problem has much, much more. So it's a wonderful question. Our students should not be just satisfied with, oh, I computed out, I find a good solution, because there are more to this question on there. It really is about how to construct these 3 points.
Another comment that occurred to me that I kind of like about the form of the answer is, if you simplify that, that's like what, 10 root 3 plus 6 root 7. So some people, their initial hunch might be, oh, so this is going to be like a 30, 60, 90, and I'm going to get like a root 3 plus a integer, or maybe it's going to be like a sine 75, and we're going to get root 6 plus root 2. But this is none of those. Like, this is not the typical form of like what you expect the area of a triangle to look like. So it's kind of an unexpected surprise there.
Yeah. Unfortunately, some people managed to find a way to guess this answer because it turns out that I didn't do a good job of selecting the answer choices. So only one of the answer choices I had was divisible by 12, and people were just like,
that's on the committee. You can blame the committee.
Yeah.
Blame them.
So, oh well.
Okay, so now let's move on to the third one. Is that okay, everyone?
Zooming, but can we talk about your approach? Because I thought about it the same way.
Oh, my approach is you go to the center, and then from the center to P1, you know it has to be 60 degrees. So
you want me to stop the screen share?
Yeah, I stopped it and...
Oh, you stopped, okay.
I didn't know you could do that.
I can share with my diagram here and let students do it. If you allow me to share the headlights over there, sure. I can do it over there. I can use mine if you want. Right? So my solution, I think I don't want to spend too much time on this because we have other questions to talk about, and this could let our students to do, is this one, and this one.
This is 4.
I still use the center. This is 4. And this has to be 60 degrees. Because this is a split. Everything has to be symmetrical right here. So, and you should know this length, because this length coming from the original 3 centers. So this length is known, and this is 60 degrees, and this is 4. So basically, this triangle.
Oh, that's really nice.
And then you can compute anything you want. Use law of sines. Well, this is again the side angle thing, but this is acute over here, so this is kind of like determined.
I see. Yeah.
I mean, the longer the side is this. The vertical side is longer, so there's no second configuration.
Yeah. And the vertical side is easy to compute because you already use the 888, so this side. So then you can compute. And this is 60 degrees, so basically you can do everything about this triangle to find this length.
Yeah, law of cosines.
Yeah, law of sines.
Some people mentioned in the
chat.
But
this solution is nothing nicer compared to the solution David showed us, right? Because that one basically doesn't need much, any.
I mean, I think they're both nice in different ways, right? Like yours like like crucially uses the quote unquote spiral similarity hidden in the diagram to completely like extract two really important side lengths and a really important angle to basically get what you want. Whereas like my solution is a little more, well, not my solution. The solution that I'm presenting on behalf of whoever actually came up with it is a lot more elementary, but a little bit trickier. I in particular, I don't think that drawing the projections is an obvious thing to do. It's definitely motivated, but it's not. It definitely wasn't the thing that I came up with. So
yeah. Okay. So good, everyone. We can move on. Ivan, you can show us the third question.
So the next question you guys should be able to see on the screen, and it's a reasoning question. David, maybe you can read it for us.
Oh,
if you can
okay.
see it.
Sure. For t greater than or equal to 2, define s of t as the number of times t divides into t factorial. We say that a positive integer t is a peak if s of t is greater than s of u for all values of u that are less than t. Prove or disprove the following statement. For every prime p, there is an integer k for which p divides k and k is a peak.
Okay. So maybe we should understand this problem. S of 2 is 1, right?
Yes.
And S of 3 is 1, and S of 4 is 1, and S of 5 is 1, right? The first interesting thing is S of 6, which means S of 6
should be 2.
2, right?
Because of the powers of 3.
Mm-hmm.
I think in general, you might my guess is that you only really care about the primes, like the largest prime factor somehow. I mean, this isn't always the case, but it seems like it's a good heuristic for problems like these. So, actually, no, that's not necessarily true. You might have to worry about prime powers. Yeah. But yeah, for small values, it's going to be like this.
So at least we understand 6 is a peak, right? And we still don't know the structure of the peak. What is it? Is a prime power? Is it product of some
Ivan,
prime?
can you even slow down a little bit? Let's compute a few more. And with a little bit more details in computing in them. For example, S7, S8, S9, S10, how do we compute?
Well, S of P is a prime. S of P is always equal to 1 right. For any prime P, because P is the first instance of that factor.
Yeah. So for example, what's S of 8? What's that look like?
S of 8 is
2.
8 factorial is divisible by 2. Yes, S of 8 is 2.
Yes, because well, let's expand that computation for a little bit. There are 7 powers of 2 in 8 factorial. You get 3 from 8, so you get 2, 4, 6, 8. That gives you 1 plus 2 plus 1 plus 3, which is 7 powers of 2. 8 has 3 powers of 2. Yeah. So you can divide it into it 2 times before you get stuck.
Mm-hmm. So how about let's say the compute f of 12? What does the numbers look like? How do we compute?
S of 12.
I think it's better for you to show us more details instead of suddenly a number. 12, you need 12 factorial, right? So it's really not that easy now.
So we have 12 factorial, and we care about 2 squared times 3, which is 12, right? How many times this divides 12?
So you want to do the 2 factors of 2 and factors of 3 separately, right?
Right.
Factor of 2 is 6 plus 3 plus 1. That's well, I should probably explain. Yeah. So if you want to find the power of 2 to goes into 12 factorial, you do 12 divided by 2, and then 12 divided by 4, 12 divided by 8. All of them like floor, of course. Yeah.
Mm-hmm. So that
if you don't understand where that formula comes from, work out a few examples, and it should be at least somewhat intuitive. what exactly is being counted at each step.
Because 12 divided by 2 counts how many 2s are there, right? And the 12 divided by 4s counts how many 4s. So you add it one more time for 4 because each multiples of 4 counts 2 2s. So 2 to the 10th and 3 to the 1.
3 to the 5. Right. So we have this number.
Should be
It's
4.
this,
Well, it
right?
should be 5 actually.
It's exactly 5.
Wow, that's a pick.
Well, you didn't
Okay.
verify S of 10, but S of 10 happens to also be 2.
Yeah.
Okay, S of 10 is 2. Okay.
So 12 is the first peak, right? First becomes a peak.
Well,
6 is
6 and
6.
12.
It's a peak.
12. Yeah.
So all the peaks are divisible by just 2 and 3, right? Because 2 is also a peak in some sense.
Yes.
Yes. S of 2 is 1 is the first one. And S of 10 is 9, right? Sorry. So
So we
for
start
every
to understand what this problem is talking about.
yeah. So we want to show for every prime p there is an integer k for which p divides k and k is the peak. Is it true or not?
Or maybe it's not true, right? Because it looks like I only see 2s and 3s.
Yeah.
Yes, maybe you pick a 7 and there is no peak that is divisible by 7.
I mean, maybe it's all multiples of 6. I don't know.
Well,
if it's all
multiples
multiples
of
of 6,
6.
then the thing would be true. But it's not obvious to me that it's all multiples of 6.
So like
No,
kind of
definitely not multiple of 6. You have S2, right? Well, we don't know.
does peak has always this form, or peak can have forms like
Divided
different.
by other numbers.
Mm.
Well, make it easy. Just even say 5 or 7, all right?
Yeah, 2 to the something, 3 to the something, 5 to the something.
Well,
Yes.
maybe we can heuristically estimate this value of S of t, because like if we just ignore the floors when we're computing, we're basically computing geometric series.
Yes.
And we're not off by that much, I'm pretty sure. So that's one thing that we can try.
But maybe
Can you write down the equation then? So I guess
Alex, wait. Maybe you can share your screen and we will try to solve this problem on your screen. I think that would be better. Can you share one?
sorry, David was able to, so I'm pretty sure I can.
Somebody
Just click on share screen. It's the green thing at the bottom. There
Okay,
you go.
cool.
There we go.
Okay, so
somebody from the attendee says maybe it's 3 times 5, 5 times 7, 7 times 11.
Oh.
See,
what is
3 times 5 is.
I think we should have a 2.
Well, 3 times 5 only goes into 15 factorial 4 times, I believe, 3 times actually, because 5 only goes into 15 factorial 3 times.
Yeah.
yeah, so I guess the question Yannick brought up was, what is S of t approximately? Well, we know our formula only works for primes, so we probably want to write t equals, well, what's the general form? It's p of 1 to the e of 1 Okay, that reads pretty terribly. I'll just write it. T equals p of 1 to the e of 1 p of n to the e of n. Right?
Yeah.
So given this, so what is t? So what is S of t? So S of t is equal to what? Well, it's like you have to consider the number of times each prime divides t factorial, right?
Mm-hmm.
So it's going to be the max over I of the number of times P of I to the E of I divides T factorial, right? Oh, that was not what I meant to do. Which is equal to the max over I, which is approximately what is this approximately? So we're considering now prime P, right?
So we divide
max
T by pi
of T.
Sorry, shouldn't that be a minimum?
Yes, I also think.
Oh, it is a minimum. You're right.
Yes.
Yeah.
So among all primes, we choose the minimum number that it divides T factorial, right?
Yeah. So this is kind of like T over Pi plus T over Pi squared. That's da da da. Which, as Yannick points out, is a geometric series. So it's minimum over I of T over. This one's a bit annoying. Use the pencil. Use minimum over I of T over Pi minus 1. And then we missed something, right? What did we miss? We missed this E of I thing. Because you see, this number counts the number of divisors of Pi, right? But you want the number of divisors of Pi to the power of EI. So you want to multiply this by apparently I can't move the text very well. So
There's an undo button.
That's fine. I mean, it's fine, I think. I mean, you just need to write here. So we also need to write an E of I here, right? Because it's a number of factors of P of I to the E of I. So I wrote a complicated equation. How does this help, if it helps?
I think if you want to write a rigorous proof, you need to say this is your upper bound, and in a similar way you can write there is a lower bound, like this only minus log of something, right?
Yeah, but I mean, I feel like we can just like start with the approximation, right? And like,
okay,
sure. I mean, it's sure like there's some error term, so it's actually this term plus an error term that's like it should be small, right? As Ivan points out, it's like sort of like log, just because in each of these terms you're going from this T over Pi to the floor of T over Pi, where you lose at most 1, and you lose that at most like log of T times, right? So there's some error term that we can write out later. But what happens here?
Well, T is the same in the numerator, so we just need to maximize the denominator, basically.
Yeah. Sure. So I changed them into a max. So when does S of T look very big? Well, we pointed out like S of T looks very small, right, when T is a prime. And that's just because it's kind of like this Pi minus 1 term dominates, right, when P is a prime.
Oh, so I guess you want it to be highly composite. And I think one of the things that 2 and what did we say our peaks were again? 2, 6, and 12?
Yeah.
Okay. Yeah, you want these things to be like highly composite. And I guess that maybe like doing some either high powers of 2 or high powers of primes or products of lots and lots of primes is sort of going to be the way to go.
Mhm.
Like, because you want the way that I'm looking at this is EI times PI minus 1 is based on an individual prime only, whereas T is going to be a product of a bunch of primes. So your one approximation on the P sub I can be bad, and that's okay as long as you have a bunch of other primes that are sort of covering up the error term. So maybe that might give you something that will lead to some success.
Mhm.
Yeah, so I guess the hard part of this problem is also like you need to figure out what it means to be a peak, right? Because like we have this like really good understanding of what SFT is, right? SFT is like approximately this expression. We sort of know the error term. We always know how to compute SFT given any t. But what does it mean for t to be a peak, or for SFT to be maximized?
Mm.
I mean, so I guess one intuitive step maybe is kind of like, okay, so let's say t is a peak, right? And let's say like there's p doesn't divide t. So let's assume t is a peak and p does not divide t, right? Well, we don't need that t is a peak for this, but what is S of pt? S of pt is probably approximate S of t, right? I just said, I'm sorry, p times S of t.
P
Right?
times S of T. Mhm.
Because I mean, the intuition is kind of like, okay, so I have like this term here, right? I'm just going to draw a box that is colored over it. Sorry, my phone. So you basically here, like, okay, so if you replace t by pt, well, it just multiplies by p, right? And this term, probably some other prime is already like bigger than p, because the p only contributes like p minus 1 to this part, the maximum, right? And hopefully like another term will contribute more than p minus 1. So hopefully S of pt is like around p times S of t. But does that mean if t is a peak, then pt is also a peak?
Mm. Yeah, PT now.
Well, I mean, is there a counterexample? I don't know. I think 30 is probably not a peak, right? Maybe 30 is a peak, actually. I don't even know. I'm just trying to spin up some counterexamples. Okay, I mean, like you can have like very obvious counterexamples, like okay, so like six is a peak, right? And I'd say p is like around 1 million. It's like a huge prime. But then S of pt is actually 6. It's not like
Mhm.
1 million. So sometimes this approximation doesn't work. But the question is, can pt not be a peak? So I think my phone is ringing on my computer, and now my computer froze. Let's do that. Okay, now it's back. Okay, so can pt not be a peak?
See, Alex, for this problem, you definitely need some time to think, because I would start with the first 100 numbers. I would find the next few picks, try to understand what's going on. Because in your expression, there is this EI power, which is combined with a PI minus 1, right? And I'm still trying to understand how do you get a peak if I want a new prime.
Yeah, so I guess for context, like when I proposed this problem, it was just something like where I just wrote down this like thing like n divides n, how many times n divides n factorial, and I was like, okay, this thing like obviously like this number should be big when it has lots of primes and primes, right? Like, but the question is like, is it the biggest when it has lots of primes? So like it's a statement that like it feels like it should just be true, but somehow you have to prove it rigorously. Oh, sorry, I was muted. Was I just muted for all of that? Sorry.
No, we hear you.
Okay. So if PT is not a peak, then what's going on if PT is not a peak? Well, then there is a number m less than PT such that S of m is greater than S of PT, right?
Yes.
Which is approximately P times S of T. I'm just going to be very loose, right, with this. So this means that S of m divided by P divided by PT is greater than S of T divided by T, right? So S of m divided by m is greater than S of T divided by T. Okay, so I wrote down some equations. They are pretty unmotivated. So why did I write down these equations? Well, the first equation is like you can sort of see the motivation, right? It's like, okay, if PT is not a peak, you have m less than PT, you just write down the only condition that you have, and then you use your approximation for S of PT, right? And then the next two equations are I want to make things sort of symmetric, so to speak, because, well, it's kind of like if I had this equation at first, then I want to get to this because now you're just considering the quantity S of m over m versus S of T over T. So this is somehow symmetric between m and T. So, and you see the logic follows, but the motivation behind this is to get an equation that's symmetric. So the question now, how large can S of m over m be? Well, the answer is 1 over max over of I of EI P PI. So when m is really big, S of m over m has to be small, right? Because when m is really big, it's basically like, okay, obviously I'm like doing abusive notation where I'm having m have the same factorization as like whatever t or whatever, right? But the point is when m is big, like m has to have at least one prime factor contribute at least something, right? It's like you have to have at least one pretty big prime factor or one small prime factor contribute a lot of times. And both of those make this thing big, right? So it's kind of like S of m over m has to be, or like, it's always bounded above based on what m is, right? So now it's kind of like the path is clear. It's kind of like, so now it's kind of like we start with a peak t that does not such that t0 such that p does not divide t0, and t0 is big enough so that the approximation holds, right? The approximation, I will descriptively draw another green box here and draw an arrow to here. Right. So now our procedure is.
Wait, Alex, use
Yeah.
the max of I for, what do you mean approximation holds?
Just this approximation here. Okay, I'll draw the bigger green.
Okay. For the prime factors of of t0, right? And for exponents of those primes.
Yeah. So like this formula for t sort of holds within enough margin of error. And I guess I haven't talked anything about the margin of error just because it's something that's more analytic. So I guess for context, I proposed this problem to a contest called the CMO Repechage, where it's kind of like, so in Canada, we have the first layer of math competition called the Canadian Open. Everyone can take it. Then we select people for the Canadian Math Olympiad. So we select 50 people, but for the next 150 people, we give them a take-home test to determine maybe 30 more candidates for the CMO. So this problem is intended for them to solve in 1 week. So sure, I'm like glossing over the details, but this is like a 1 hour, this is a 1 hour session. So if you're at home, like you can work out the details, you can convince yourself that the approximation holds. And maybe if you're solving this in real life, live in the contest, well, you have to figure out what this approximation is. But basically the path forward is now, so assume p times t0 is not a peak, right? Then there is a peak t1 between t0 and p times t0, right? Well, why is t1 between t0 and p times t0? Well, it's because if t1 is less than t0, then of course s of t1 is less than even s of t0, so it can't be greater than s of p times t0, right? So now s of repeat with t1. Okay, so if p divides t1, then done. So assume p does not, so repeat with t1, and then get a sequence t0, t1, of peaks. They become larger, and s of t0 is less than s of t1 over t1, less than .
Mm-hmm.
But I mean, this sequence is like obviously infinite because there are an infinite number of peaks, right? Okay, it's not obvious there are an infinite number of peaks, but that's left as an exercise. There's an infinite number of peaks, so we have an infinite sequence of peaks here by our assumption that p never divides any of the peaks. They become larger, and this s of t0 over t0 becomes larger as well. But when t0 goes to, or when t goes to infinity, s of t over t has to go to 0, right? It's always bounded above. So this eventually will lead to a contradiction. But this is a problem because there is some number m such that for all, let's make the number m big because it is a big number. For all n greater than m, s of n over n is less than s of t0 over t0, right? Yeah, so I guess I wrote a lot of text, and well, basically you want to just, it's kind of like saying if t is a peak, then pt is probably going to be a peak, but it's kind of hard for you to prove that because it's hard for you to consider all of the numbers between t and pt. So you sort of cheat by like just creating this infinite sequence and finding some constraint on like the numbers within the sequence. Because it's kind of like maybe t is a peak, but it's like a very low quality peak, quote unquote low quality, defined by something like s of t over t, right?
Alex, I do not get your last part. Why there's a big M such that for n bigger than m, this ratio is going to be less?
So it's basically like, so s of t0 over t0 is now fixed, right? Let's just call it epsilon for now.
Yes.
So I'm claiming that when m is really big, then s of m over m is really small, right? So I'm going to draw the logical boxes here.
Yeah,
So I'm going to,
I see.
yeah, so this is a logical step here.
Mhm.
Where basically it's like if m is really big, then either you have like M has to have a small prime factor with a lot of factors, or it has to have a really large prime factor. Because if it doesn't have either, then like it has a bunch of small prime factors, a bunch of small powers, so it's bounded, right?
Yeah.
Does S of t over t actually go to 0 as t goes to infinity? Can you prove that rigorously, or is that not true?
Well, the approximation is upper bound, right? And you see like the max is like so like if it's upper bound, then we basically need like or like if there's like a lower bound that like S of t divided by t needs to be satisfied, then we basically have an upper bound on the max of EI times PI minus 1. So since EI needs to be at least 1, that gives a bound on what PI must be. Like what kind of PI can be, and for each PI, there's a bound on EI. So yeah, so there can only be this many prime factors, and each prime factor can only divide into the number this many times. So that gives us the bound.
It converges to 0 really slowly, but it does converge to 0.
I can type a few questions for our audience to think about based on what you said. Should there are infinitely many peaks? I think this is a nice tiny question. And the second one, am I understanding right? Limit as m goes to infinity.
Ivan, are you going to share your screen? I can stop sharing mine.
No. I think I'm typing on your screen. Can you see it?
No.
No.
No, I'm not.
Oh,
now I see.
Now I can. Yeah.
Is it true?
Okay. Yeah.
So we want to show, as you said, there are infinitely many peaks. I think this is one reasoning they can think about. And the second one, you're saying limit as m goes to infinity of S of m gets smaller and smaller and smaller, right?
Well, it sometimes gets bigger and then smaller and bigger, but it goes to 0.
So this is a correct statement.
Yeah. And basically it's like, yeah, if for any epsilon, like S of m over m is eventually less than epsilon. So I guess I glossed over both of these facts, and I'm claiming they are quote unquote obvious, but they're not that easy.
But the whole map is so good, right? His proof. He started with something like this and it goes to Sm over m it's the thing he want to compute. And that's his very good function to deal with. Okay, so Ivan, we will do this. We will post some questions and then we will visit this one, right? This one was a lot of details there are lots of details worth for us to investigate. And we're about 9 and we're already over, so we will stop at here. How about that?